Okay, in this part, we're going to discuss the zTransforms for digital signals or digital sequences, and then look at the definitions of zTransform and the properties, and how to find the zTransforms. And also from there, we want to use zTransform to discuss system stability in discrete time domain. And then we're going to finish that part off with the inverse zTransform. So if you have, for example, a sequence in Fk brackets there, okay, say we have a set of, we have a continuous time signal, we took a sampling process of that signal, we end up with a sequence. Okay, so sequence will have elements of 0, F1, F2, F3, and so on. It goes on because time tends to infinite, therefore the sequence will have infinite number of components. The definition of a zTransform is actually a lot simpler than that for the Laplace transform. What happens here is that we introduce a z variable, which is a transform variable for digital systems. A z is a bit like an s, but they represent a different thing. Okay, it's only used for digital systems, like s being only used for continuous time. Okay, in the next slide, I'll explain what that z represents. But for the time being, if you look at the second equation on this slide, the zTransform of this sequence is basically a summation of each component times different z. Okay, so the first element, the first component here, f0, will be multiplied by z to the power of 0. This one, f1, will be multiplied by z minus 1 to the power of minus 1. This one multiplied by z to the power of minus 2, and go on. So, and this negative power will go up. So that next component will be z minus to the power of minus 3, and the next one will be z to the power of minus 4, and so on. If you add them together, after you multiply, you add them all together, that will be the zTransform of that sequence. So if you know the sequence, finding the zTransform of that sequence is pretty straightforward. Okay? The only thing now, the key thing here, is try to understand what z minus 1, z minus 2, z minus 3, and so on mean. Okay? What they really mean. And what is that? Instead of s. S we know it's a complex frequency, but what is that then? So I'm going to use this example here to show, actually to help and explain what z is. Okay? Say I have a sequence. I have a sequence in this graph. Okay? So the value expressed is in equation 1. So I have a value of 1. The first one is 1. Second one is 2. Third one is 1. Fourth one is 3. Okay? And before time equal to 0, they are all zeros. So I'm not too worried about that. If I apply the definition of the zTransform to that particular sequence, the first number is multiplied by z to the power of 0, which is 1. This number 2 is multiplied by z minus 1. This number is multiplied by z minus 2. And this number is multiplied by z to the power of minus 3, and so on. Okay, that's the definition of zTransform. And then we got really no doubt about that. I can, if I have more values, I'm going to just continue write that value. Okay, so suppose that sequence is xn. then Z transform of that, I will say XZ. That's in equation number 2. Next thing I'll do is that I'm going to shift this xn towards the right hand side by 1 interval. Okay, so I move everything towards the right by 1 interval. Okay, so this 1 is moved to here, this 2 is moved to there, this 1 is moved to there, and this 0 is moved to there. So I get 0, 1, 2, 1, 3. Because I've shifted the whole thing towards the right hand side by 1 interval. And say this new sequence is either xn minus 1 because it's a shift of this, or I just say it's x1, we just give it another name. Okay, so the sequence will be 0, 1, 2, 1, 3 instead of 1, 2, 1, 0. So the only difference here is you have a 0 in front. This sequence is basically the xn delayed by 1 sampling interval. Okay, that's why we use xn minus 1 means delayed by 1 interval. Now, if I apply the definition of Z transform to equation 3, okay, first number times z power of 0, so that's 0. This number, this is the second number, so it needs to be multiplied by z to minus power of minus 1, so 1, z minus 1. This number here multiplied by z minus 2. This number, z minus 3. This number, z minus 4. Now, if you look at this, what we have here, if you look at this, this is 0. Okay? Now, the rest of the terms will have a common term, z minus 1. So, can take that z minus 1 out of bracket. There's z minus 1 here, because that's minus, it's z minus 1 times z minus 1. This is z minus 1 times z minus 2. This is z minus 1 times z minus 4. So I can take that z common term out of the equation. So z minus 1, then bracket 1 plus 2, z minus 1, 1 times z minus 2, 3 times z minus 3, and so on. That's in the bracket. If you look at the bracket, if you look at here, what is in the bracket compare with the right hand side of equation 2? That is exactly the same. Okay, so from 1 to here, same as from 1 to there. So really what's inside the bracket is my xz. So therefore, I have this relationship in the equation number 4. The Z transform of delayed sequence is Z minus 1 times the Z transform of the original sequence without delay. In other words, the sequence, the Z transform of sequence times Z minus 1 means the sequence being delayed by 1 interval. That means, so Z minus 1 basically means, if you multiply something by Z minus 1, Z minus 1 represents a delay of 1 interval. Positive power would have the effect of moving advance. That means moving the sequence towards the left hand side by 1 interval. But Z minus 1 means you're delaying it. Okay, therefore Z minus 2 will represent a delay of 2 intervals. Z minus 3 would represent a delay of 3 intervals. So that's really the definition of a Z here. Okay, it's fairly straightforward. Okay, let's look at some examples of Z transforms. Because the definition is so straightforward, so finding the Z transforms is not that hard. So if I have signals with finite non-zero samples, so for example, the only non-zero sequence in this No, sorry, the only non-zero numbers in this sequence is this, the second one and third one. All the others are zero. Then the transform becomes very, very easy, because the first one is z minus to the power 0. This number 3 times z minus 1, 2 times z minus 2, and all the rest will be zeros. So I only have two terms here, 3z minus 1 and 2z minus 2. Sometimes it happens, you have a sequence with finite number of non-zeros. So I can take z minus 1 out of this, I get, after bracket, I get 3 plus 2 times z minus 1. Now I can convert this into positive power, just reorganize that, okay, multiply z squared to the numerator, denominator, I end up with this. So fz, this is just, equation 4 is the same as equation 3, just that I reformatted it, okay, by multiplying a z squared over z squared, okay. Now, like Laplace transform, like transfer functions in continuous time, we also have the definitions of zeros and poles. So in this case, if you equate the numerator terms, it's the same way, okay? You equate numerator terms to 0, find the solution of that. That's your 0 in zTransform. If you equate the denominator terms to 0, and you get your poles. So for equation number 4, or for the zTransform of fz here, equate the numerator to 0, 3z plus 2 equal to 0. That will give me minus 2 over 3. That's my 0, so I have 1 0 there. Equate the denominator term to 0, that's z squared equal to 0. That will give me 2 poles at z equal to 0. Now, we have the same similar definitions. We have find zeros and poles for z transforms, but they don't necessarily mean same thing for stability, okay? In the continuous time, we want the negative poles for systems to be stable. And if you have poles sits on the imaginary axis, then you have a marginally stable system. This is different, okay? But I will talk about that next time in the second section. In the second session, I mean. If we have a unit pulse signal, that is the sequence equals to 1 at only one point only. That's when k equals to 0. Or the other point, it is 0. So that's, if you apply the zTransform to that, that's straightforward. The first term times power z to the power of 0, that's 1. All the others would be 0. So zTransform of that unit pulse sequence is 1. Now that's a bit like, in a way, you can compare that with the impulse signal for the Laplace transform. Okay, for the Laplace transform, the impulse signal delta t will give you a Laplace transform of 1. Now this is very similar to that. Okay, so that transform of that is 1. If I have a unit step signal, that's the case where the sequence, the discrete time sequence, has a constant value, regardless of what k value you have. Okay, so k equals to 1, 0, 1, 2, whatever, the fk, the sequence will be 1. Now you can apply the zTransform to that, and so this becomes a 1 plus z to the power of 1, because the value is 1. Then this is 1, the third value is also 1, so it's 1 plus times z to the power of minus 2, and then plus 1 times z minus 3, and go. Now when mathematically we can prove it, if this z converges, then it will equal to this. Okay, it's a bit of math, but we don't get worried too much about that. Okay, it's 1 over 1 minus z power of minus 1. Now I can, to find the zero and the poles, I can actually do a little bit of reformatting. I'm going to times top by z times every term in the bottom by z. this will end up with z over z minus 1, which will give me a 0. If equate the numerator to 0, give me a 0 equal to 0. It's a bit fiddly, but that's what I mean. Equate the denominator terms to 0, that will give me a solution of positive 1. That means I have a pole at z equals to 1. Now, from step 2 to step 3 is something I've done deliberately because I want to find the zeros and poles. But in general, we like this format better, especially for the design of digital controllers, because z minus 1 represents a delay, where z represents advance. Now, in real life, you don't know. You might, if you delay, you know what happened in the future, in the past, but you don't know what will happen in the future. So we don't like the advances. The only reason why I'm doing it is because I need to find the zero and the poles. But in general, we like to keep them in the negative power, which is better. By the same approach, we can actually find the z-transform of a unit ramp. That's when the signal goes up with time. And again, the z-transform, I'm not going to go through that mess. The z-transform can be expressed in the negative power of z or positive power of z. I only need a positive power of z for finding 0 and the poles. Okay, equate numerator to 0, it will give me z equal to 0. That's my 0. Equate the denominator terms to 0, it will give me two solutions, but the same value. So z equals to positive 1. Exponential functions, they come into two formats. I just separate them to slightly differently. Now, one is positive power, one is negative power. Now we know the Laplace transform of EAT is 1 over s minus a. The Laplace transform of e to the power of minus at is 1 over s plus a. But the z-transform of that sequence, of the sampling sequence of this positive power, okay, sampling process, remember, is to equate that t, small t, by k times capital T. And the only variable here is that small k, because k changes with, k is a series of integer numbers, t is my interval, which is fixed, a is the value for the exponential function. Okay, it's also a value. So therefore, this is really E, A, T, and then put a bracket outside the power of k. Okay, so the only variable here is the sequence k, sequence number. The z-transform of that, if I use the negative power, it's 1 over 1 minus EAT. Now, EAT here is a number, remember. A is a number, T is a number, e to the power of A times T is also a number. Okay? So you can see this, as an exponential function, but it's not a function at all, it's a number. If you know A and you know T, then you will be able to calculate that number. Okay? If I want to use the positive power for the z, then I'll multiply z to the numerator and denominator, I get z over z minus EAT. Therefore, I have a 0 at 0. I have a pole at positive e power at. For the negative power of exponential function, now in the Laplace transform, that will give me a 1 over s plus a. But in the z-transform, this, for the positive exponential function is a 1 minus something. For the negative exponential function, it is still 1 minus something. The only difference here is this. Instead of e to the power of 80, we have e to the power of minus 80. Okay, so the only thing changes is the value before the power of z power of minus 1. Again, we can actually convert that into positive power, so multiply z to the numerator, and every term in the denominator, I get z over z minus EAT. So you can actually have a look here. That transforms the difference is this number. Okay? And I have therefore I have a 0 and 0. I have to put at e to the power of minus AT, which is this number. Okay? So don't consider the second term in the denominator as a function. This is not a function, this is a number. This is a number. Okay? The only time you can consider it is a function is when you have a variable there, something that's not fixed. So like small t in the time domain, it changes with time. This small k in the discrete time, because k is a sequence number. Okay, it changes from follow the integer pattern. Some of the properties for zTransform: linearity. If you have zTransform of one sequence and zTransform of another sequence, you can add the two together. Okay, if you add the two sequences together, then you can add two zTransforms together. If you multiply one sequence by a factor of a, then its zTransform is also multiplied by a factor of a. It's a bit like Laplace transform that we did before. Okay, it's because we are only dealing with linear systems. Okay, I can use that property to find zTransform of some more complex signals. For example, I have a cosine omega t, small t for the continuous time. So if I replace small t by k times t, capital T, I get that sequence. Now, how do I find the zTransform of that? Do I have to find the values every time and then multiply by z to the power of whatever? We don't, because we know the zTransform of exponential function. And we know the relationship from your maybe A-level math. We know the relationship between sine, cosine functions and exponential functions. And in fact, cosine omega t would equal to half of exponential j omega t plus exponential e to the power of minus j omega t. Okay, we know that from our math. So if I know so I can derive equation 2 from equation 1. Okay, for any k that's positive k, this will stand. This is the same as that cosine. Now, from previous page, from this one, we know the zTransform of exponential functions. Okay, so really this linearity property of zTransform will give you all sorts of possibilities. Okay, so over here, if I can find the zTransform of this exponential function, I find zTransform of this zTransform of this function, then I can add them together, divide by 2. That would be the zTransform of my cosine function, or cosine sequence. So this, take that k out, because k is the variable here. So inside it's e j omega t, then bracket power of k. The zTransform of this would be z over z minus e to the power of j omega t, except that k. Okay, k disappears after you apply the zTransform. This is the same, z over z minus e to the power minus j omega t. Take away that k. K is a sequence. It disappears after you do the zTransform. It's a bit like t disappears after you apply zTransform. Sorry, the small t in continuous time disappears after you apply Laplace transform. You end up with s's, not t's. Over here, K is the equivalent of T, Z is equivalent to S. So you should end up with Z, not K. So this now becomes a function of Z. You can actually find the common denominators and put them together in this form. So that's okay, because these are two fractions. I can actually find the common denominators. I can reformat it. I end up with something like that. Now this will give me a couple of zeros, a couple of poles. Okay. The reason I'm doing that example is to show you actually can use that linearity property to find more the Z transform of a more complex signals. You can do sign if you like, okay, if you want to try. And time shift, that's something I already explained at the beginning when I introduced the definition of Z transform. So if I have a sequence, fk, this Z here means apply the Z transform to fk, I get fz. Then if you delay that sequence by n number of intervals, okay, if you delay the sequence by n number of intervals, the delayed sequence, if you apply Z transform to it, will equal to the Z transform of undelayed sequence times Z minus to the power of minus n. That's really the definition of Z, you see. Z minus 1 means delay of one interval, Z minus 2 means delay of 2 intervals, and so on and so forth. So if you delay by n intervals, then of course the Z transform will have to be multiplied by Z to the power of minus n. So n just any interval number. So with that property, I can give you another example here. What I want to find is the Z transform of the following discrete sequences. I have a sequence here, 2 plus 3e to the minus 2k. Okay, already done the sampling process. So now it is a discrete sequence. I want to find the Z transform of that. 2, consider that 2 times 1. 1 is my unit step sequence. And the Z transform of that, if I just go back a few slides, is Z over Z minus 1, or 1 over 1 minus Z minus 1. So this is the kind of stuff you need to actually bury in your head. Okay? It helps at least to speed things up when you try to solve these problems. So it's Z over Z minus 1. Second part is 3 times the exponential function. Now exponential function is Z over Z minus e to the minus 2. So you take away that k, so that becomes e to the minus 2. Now e to the power of minus 2, if I do the calculations, it equals to 0.135. So I have two parts. This part is the Z transform of that 2. This part is Z transform of this 3 times e to the minus 2k. Now you might say, well, where is the capital T? That's the time interval, because I already tuned the value. I put values in there. So that 2 includes a, and this 2 is actually equals to a times capital T. Okay? So you got that, and if I want to find the zero and the poles, notice that I started with positive Z because part of my question is that I want to find the zero and the poles. If you multiply, you find the common denominator of these two. Okay, for this first term, I need to multiply Z to the minus Z.135 divided by Z minus Z.0.135. For the second term, I need to multiply that by Z minus 1 over Z minus 1. So I have common denominator for the two terms. And then I can add the two together. Okay, that will give me this equation number 5. Equation number 5 From there, if I equate the numerator terms to 0, I find two zeros. One equal to 0, the other one equal to minus 0.654. I can find two poles. One is 1, the other one is positive 0.135. Okay, so here I applied the properties of the linearity property of the zTransform, and I need to know the zTransform of the unit step sequence, and I also need to know zTransform of the exponential sequence. Okay, and then everything else becomes fairly routine. Okay, you just apply the definitions, and then you find the common denominators and put them together, and then afterwards you find zeros and the poles. Now, the thing I wanted to emphasize here is exponential functions. Exponential sequences in time domain remain as exponential, but once you convert that into zTransform, it becomes a number because the k doesn't exist anymore. E to the power something or a number. Same goes here for this. So 0.3k. Now, if I want you might get scared and you say, "Oh, I know exponential zTransform exponential function, and I know step." And the professor may also talked about ramp as a sine wave, cosine wave. What about this? I don't have an exponential, but it is exponential in a way. If you think about 0. to the power of k, that is a sampled consequence of exponential function. So think about this. Right? What's in the green block? Fk equals to EAKT. That's a sampled exponential function. It's just that EAT is a number. Because A is a number, T is the interval, that is also a number. So I can replace EAT part in the zTransform of the exponential function by 0.3. So if e to the power of AKT gives me the zTransform of that z over z minus EAT, this whole thing here, or this whole thing here is 0.3. Therefore, zTransform of this is z over z minus 0.3, if I use the second part of that, or 1 over 1 minus 0.3 times z to the power minus 1. Okay, consider that. So we have a lot of flexibilities here. It's a number, okay? Because E itself is a number, okay? It's just expressed for engineering purposes in continuous time when we actually keep the E there. But essentially, it is a number. So from there, I can find 0 equals to 0 and pole equals to positive 0.3. Okay? That's really the zTransform of that. So consider this 0.3 as e to the power a times t if you want to use a formula for the zTransform of the exponential function. Okay, some practice questions for you. Let me just try to reorganize that because it's probably just not long enough here. Okay, and I want you to work out the zTransform of these sequences. Okay, thank you.